So it's my pleasure to introduce Yichen Chen. Peter came from UCLA wanting to do APIC method.
Sure.
We're very excited about the APIC fluid method. And he saw that we were working on granular materials, and I said to him, there's some APIC in there somewhere.
Yes.
And so he started working on granular materials with Ken Cameron and myself, and working on material point and discrete methods there. But it soon became very apparent that Peter's interests are very broad and that he's very adventurous. So when the opportunity came along to work on food printing with Todd, Professor Lipson, and maybe even try his fingers in machine learning there, he said he really wants to kind of venture out in that direction, and then convince Chen and I that there's room for machine learning in that project. And I guess that got Peter's appetite going for machine learning. And so when he finished working on the granular materials, he said, I want to try to bring more machine learning into my research. And I said, that's a whole other PhD. Are you sure you want to do this? It's high risk. He said, yes, I want to do this. If I don't do it now, when am I going to do it? I said, okay, let's go for it. You're taking on a risk, but I'll support you. And Peter has since then developed the whole, I think, machinery with a bunch of students working on different projects that intersect machine learning and simulation. I'm guessing we're only going to see a subset of projects in today's presentation, but I just want to say I'm really impressed with the breadth of the work that you've undertaken and the courage with which you've undertaken it.
Yeah. Thanks for the introduction. Great. So this day finally arrived. So today, I'll basically share with you guys what kept me occupied for the past 6 years. Hopefully by the end of my talk, you will share the same excitement for physics simulation as I do. Physics simulation computationally models physical phenomena. On the left, we're watching a real rubber rod being injected onto a conveyor belt. On the right, we're seeing a computer simulated digital counterpart. The simulated physics is very accurate, capturing the signature cooling pattern. Having a predictive simulation, like the one on the right, allows us to study the dynamic behaviors of elastic rods without painstakingly setting up real experiments. All you need is a computer. And once we have a physics simulation, another thing we can do is design. In this bunny joint example, we want to figure out the optimal placement for the propellers. We can design these propellers in a simulated environment and know how well they will fly in the real world. After we're happy with the design, we can then fabricate it and use them. Let's see another example of physics simulation, this time in the virtual reality context. During the COVID-19 pandemic quarantine, we all had these long video calls with our friends, families, but sometimes we just want to go one step further. We want to do something together. Virtual reality provides a great opportunity for that. Of course, a huge element of reality is physics. In this case, powered by accurate physics simulations, we can now play a game of Jenga within virtual reality. Physics simulations like these find wide applications in science and engineering, civil engineering, material science, aerospace engineering, games, animation, robotics, just to name a few. A long-standing challenge to physics simulation is computation efficiency. The simulation here is a super accurate one-to-one reproduction of a real physical experiment. The shape of each grain is obtained from the X-ray scan, so it's super accurate. Simulation has 50,000 grains. But it takes 17 hours to simulate a 480-core supercomputer. Anyone would like to guess the size of the cylinder geometry here? Anyone? Can put in the chat box.
1 kilometer.
1 kilometer. That would be great.
Half a millimeter.
Half a millimeter. That's very different. Why did you guess half a millimeter? Because
It reminded me like the strand of, like roughly a strand of hair, but not quite.
Right. So it is in fact only 22 millimeters by 11 millimeters. So 2 centimeters by 1 centimeter, and that's 0.8 inch by 0.4 inch. So it's really tiny. What this means is that if you want to simulate a typical hourglass, like the one here, right? with the grains that we see on the left, you will need to wait 610 days to simulate, which is obviously impractical. Did you guys see the hourglass? My favorite. So, unfortunately, this example is not an exception. What we often find is that simulation one-to-run is just too slow for any meaningful applications. An ideal simulation will run in real time. Maybe 5 years ago, if I can get my simulations running real time, I'll be like, job done, let's go get a beer. But these days, with the rising need of using simulations as a tool to generate data for reinforcement learning, real time is not even enough. In RL applications, we often need to run simulation with thousands of parameter instances. Even if each simulation runs in real time, the total simulation time can scale up really quickly. That's why we need each individual simulation to go beyond real time. So how do we go from weeks to beyond real time? In my PhD thesis, I propose a multiscaling approach and a machine learning approach to tackle this computation bottleneck. For each approach, we aim to be 10 to 100 times faster than the baseline simulation method while maintaining the same level of accuracy. And here's a roadmap of my thesis. We start with the discrete rigid body simulations that are really expensive to simulate. To make it faster, we'll combine it with a continuum simulation using the multiscaling approach. However, continuum simulation alone can still be too slow for real-time and beyond real-time applications. And to make continuum simulations faster, we look for the help of neural networks and propose a machine learning solution. Let's first take a look at the multiscaling approach. Here's a real footage of sand grains flowing around, and we can see the rich interaction between individual sand grains, such as bouncing and rolling. Let's suppose you want to simulate the physics of these grains in a computer. Probably the most intuitive thing to do is model each individual grain as discrete rigid body particles. We'll then explicitly detect the collision between them and compute the normal forces and the frictional forces. Well, this approach actually works pretty well. The left simulation captures the signature extended patterns, and the right simulation captures shear localization and string softening. Discrete simulation is indeed very accurate. That said, computational speed is a major concern. As we discussed earlier, the simulation of a tiny geometry takes 17 hours to run a 480 core machine. Another approach to simulation is continuum simulation. Instead of solving individual contact force between each grain, we treat the entire body as a continuum. We can then compute the internal force from a divergent stress, which is a continuous field. The continuum model is then discretized into computers using your method of choice. In this case, the material point method, MPM. Each material point models not just one sand grain, but a collection of grains. Consequently, continuum simulation is a lot faster because it uses significantly fewer degrees of freedom to model the same amount of material. But this advantage of computation speed does come at the cost of accuracy. Although continuum simulations can capture the overall behavior of the sand flows pretty well, it does not capture the surface details and the flyaway of each individual grain. Another problem with a continuum simulation is that it does not have a notion of grain size. So let's play the simulation here. So discrete simulation here correctly capture the grains getting stuck at the funnel because the opening is too small. But the continuum simulation does not. So yes, the discrete simulation is not paused. It is actively being simulated. And just to remind us, the red particles here are discretization of the continuum system. They are not actual discrete grains. The role of continuous simulation continues as the lack of the notion of grain size results in an incorrect mesh dependence physics. The larger the mesh, the thicker the shear band, and the thinner the mesh, the thinner the shear band. You might ask, why does this matter? Well, because real physical shear bands only have fixed sizes, and shear band is a precursor to many large-scale granular phenomena, for example, landslides. Therefore, capturing the correct shear band size is important, especially for the people living down here. For them, this is a matter of life and death. In summary, we face a dilemma where discrete is accurate, yet slow, and continuum is inaccurate, yet fast. Can we couple the discrete approach and the continuum approach so that we can have something that is both accurate and fast? Prior works on this topic has provided promising results. For example, Wallman et al. Combined the discrete method and continuum method so that the intruder always interacts with the more accurate discrete methods. And the rest of the simulation domain is modeled with the faster continuum approach. However, this approach, along with other prior works, suffer from a key limitation. There is no adaptivity. The discrete regions and the continuum regions are prescribed before the simulation and cannot be changed during the simulation. Consequently, this requires lots of domain knowledge and cannot take care of scenarios where the discrete zones constantly evolve. To introduce adaptivity, though, is challenging. We'll first need to answer when and where can we assign the discrete zones and the continuum zones. For different problems and users, the answers can be different. How can we derive a generalizable solution? Second, how do we convert between continuum zones and discrete zones? This is challenging because we're converting between two completely different physics, the discrete physics and the continuum physics. This is different from traditional adaptive simulations that employs adaptive resolutions. In those cases, the continuum physics stays the same, only the discretization resolution is changed. But here, we're facing a different problem. We're converting between two very different physics. To address these challenges, we propose the hybrid discrete continuum framework. We develop a hybrid oracle to decide when and where to allocate the continuum zone, the discrete zone, and the reconciliation zone. Inside the reconciliation zone, there are both discrete and continuum elements. We also introduce homogenization and enrichment operators to convert between discrete zone and continuum zone. And we also introduce a coupling principle to couple the discrete grains and continuum elements inside the reconciliation zone. With this set of tools, we build simulations that are accurate, fast, adaptive, and work in various scenarios, geometries, and experiments. So how did we do this? So first, hybrid oracle. For different problems and users, the definition can be different. Definition of accuracy can be different. For the graphics community, what's more important is probably what we see, and that is the surface details. In this case, we propose a distance-based oracle that uses the discrete model near the surface and uses the continuum model in the interior. For the mechanics community, surface details probably don't matter that much. After all, if our goal is to model earthquake, the individual sand grains flying around in the surface doesn't really matter. Indeed, the interior movements becomes more important. And in this case, we'll build a string wheel Laplacian-based oracle that uses discrete grains inside the shear band and the continuum elements elsewhere. And since the regions are updated dynamically, there'll be time when we need to convert discrete grains into continuum elements. We call this operation homogenization. And in homogenization, we need to determine the density, the velocity, and the stress of the newly created continuum element. We do so by averaging the density and the velocities of the discrete grains and use the Christopherson's formula to convert discrete contact forces to stress. This conversion was not that challenging per se, but the reverse problem is much harder. It's harder because in enrichment, we're going from the coarse scale to the fine scale, which is an inherently underdetermined problem. We propose a heuristic to get the continuum stress onto the discrete system. This technique basically applies the deformation we saw in the continuum simulation to the discrete packing. And without the deformation history, the discrete grains has nearly zero shear stress, which will cause the whole simulation to crash. And after applying the deformation, the discrete packing picks up the shear stress and can now be safely inserted into the hybrid system. The last component of the hybrid algorithm is the coupling principle. Inside the reconciliation zone, where discrete system and continuum system coexist, we solve the dynamics and enforce a constraint such that the velocities of the discrete and the continuum system are equal. And that's it. We've just gone through the entire hybrid pipeline. Now let's take a look at some results. We rotate a drum filled halfway with grains. As the system evolves, we observe the same characteristic free surface between the hybrid method and the purely discrete method. And the advantage of having explicit discrete representation is that we can now capture jamming. Here we simulate a funnel with a small opening. Our hybrid simulation, like the purely discrete simulation, jams with no problem. With a wider opening, the hybrid approach can model the ballistic motion and collision after grains flowing out of the silo. Our hybrid approach also handles the full range of restitution coefficients from 0 to 1, whereas the continuum NPM approach is basically equivalent to COR equals 0. Here we insert 4 bunnies into a pile of grains. Initially, on the top surface is represented as discrete grains. Our method then dynamically enriched the interior around the bunnies, and compared to the pure discrete approach, we use 88% fewer discrete grains and are 6.8 times faster. Not only can we do cool graphics results, but hybrid approach also checks out in terms of quantitative accuracy. In this simple shear example, both the discrete and the hybrid simulation capture the identical thickness of the shear band. By contrast, the continuum simulation suffers from match dependence and suggests a shear band thickness of 1 element size. Here we demonstrate the match independence nature of the hybrid simulation. Similar shear band thickness are observed in hybrid simulations of high, medium, and low continuum resolutions. Basically, as long as you simulate the shear band portion with discrete grains, you'll be able to capture the correct shear band width. Next is a plane indentation test. Here we have an intruder hitting a container of grains. Both the discrete and the hybrid simulations present similar characteristic log spiral shear band. By contrast, continuum simulation suffers from match dependence and produces a thick, blurred shear band. The speed-up advantage of the hybrid approach is most obvious with large-scale granular simulation that involves tens of millions of grains, where we're seeing over 100 times speed-up. Without the hybrid approach, the discrete simulation would take 10 years on our 32-core machine. So now that we have shown that the multi-scale hybrid simulation captures the previous scenarios, where else can we capture this again? What are some future opportunities? One direction is going from the circular shaped grains assumed in our work to general shaped grains. Real-world granular media are obviously not circular. Pharmaceutical pills, rocks, rods, their dynamics are very different from circular shaped grains. For example, here is a column class of rod-shaped grains. Notice the entanglement among the rods, which is not available in circular grains. And how to develop a multi-scale discrete continuum framework for these grains is still an open question. In addition to granular media, nature is full of multi-scale phenomena. Clouds can be modeled in the discrete scale as yarns, but can also be modeled at the continuum scale as thin shells. COVID transmission can be modeled in the discrete scale with individual agents, but can also be modeled at the continuum scale using differential equations. Nanomaterial can be modeled at the atomic level, but can also be modeled at the continuum level. We believe all these phenomena can benefit from our adaptive, multi-scale, hybrid discrete continuum framework. The multi-scaling approach works pretty well, but the end product can only be as fast as the continuum simulation. But what if the continuum simulation is still too slow? This is where machine learning can help. For the second half of my thesis, I'll talk about how to use neural network to accelerate continuum simulations. All continuum simulations start with a continuous model, not surprising, often described as partial differential equations, PDEs, in the following form. Basically, the PDE is a function of the spatial gradients and the temporal gradients of the vector field F. Example of such PDEs include the diffusion, Navier-Stokes, and lasso dynamics equations. To solve these PDEs in computers, traditional numerical solvers discretize the vector field with p spatial samples. For example, there are over 66,000 vertices in this piggy mesh. When p is large, computation becomes intractable, making them unsuitable for time-critical applications. There's a long history of using machine learning to solve this computation bottleneck. One line of this work is model reduction, also known as reduced order modeling, or ROM. The classical model reduction approach would take the discretized deformed positions, for example, mesh vertices in this case, and directly construct a low-dimensional manifold for them. Traditionally, people build this manifold using linear approaches like POD or PCA. More recently, people began to build this manifold using autoencoders with neural networks. So how do we actually build this low-dimensional manifold? Let's suppose we have a simulation sequence consists of many time instances. Let's zoom into one particular time step. For each individual discrete sample, we have its initial position, current position, deformation gradient, and velocity. Let's then concatenate all the current positions into a big long vector, x arrow. We're then passing these positions into an encoder function E, which outputs x hat. And we then pass this x hat into a decoder function to recover the current positions. This is nice because after training, we can just solve for the dynamics of this low-dimensional x hat instead of x arrow, which therefore will be computationally a lot cheaper. For now, so let's slow down a little bit. Let's focus on this decoder function here. Do we have a question? We're good. So let's focus on this decoder function here. We go from x hat to the discretized positions, which is a super long vector. Many great works have been published using this representation, building reduced order models for solids and fluids, and they achieve lots of amazing results. But is this really the best way? In fact, we observed that the classic approach of constructing a decoder representation has several limitations. First, it does not provide any gradient information. Therefore, such a technique may work well for a mesh-based finite element method where the gradient is available. It's not straightforward to apply to point cloud-based simulation where the gradient may not be available. Another drawback with this approach is that it only decodes information for a fixed number of discretized positions, but not at other places, for example, in between these points. Consequently, this approximation is discretization dependent, and the neural network structure has to be modified for different resolutions and discretizations. It also does not support remashing during simulation. The memory usage also surges as the number of discretized samples increases. We observed that all of these problems are really just one problem. This approximation is built for the discretization of the continuous system instead of the regional continuous system itself. And this is really the key insight I would like to convey, that this classic approach here is built for discretization of the regional continuous system instead of the regional continuous system itself. To address these problems, we propose to, instead of learning the discretized positions, we can learn the continuous deformation map itself. In other words, instead of constructing a manifold for a fixed number of points, we're constructing a low-dimensional manifold directly for the deformation mapping, which is this lowercase x function here. It maps infinite number of points from its undeformed domain to its deformed domain. Consequently, we can also obtain other kinematic information, the deformation gradient, the velocity, by simply differentiating the learned deformation map. And we can do this for arbitrary undeformed position in the reference domain, even if they're not included in the training data. This framework is also discretization independent. It supports resolution change easily without having to retrain the network. Also facilitates remashing during simulations. Furthermore, the memory usage remains unchanged even as the number of discretized samples increase. Essentially, we're able to address all the limitations of the classic approach. And I would like to emphasize that because we built this approach for the original continuous system itself, it can therefore deal with discretizations, any discretization of the regional continuous system, point cloud, mesh, grid, voxel, whatever you like. So we therefore dub our approach continuous reduced order modeling, QROM. So how do we actually build this representation? Everything in the beginning is the same as before up until now. Next is what we do differently. We pass this x hat here as an input to our decoder function G. Another input of the decoder is the initial positions of these discretized samples and uppercase X. And for different discrete positions, obviously the initial positions are different. And the output of the decoder is the current position. Additionally, during training, we'll also enforce the gradients of the decoder function to be consistent with the actual deformation gradient and velocity. Basically, we're training both the neural network itself and the gradients of the neural networks. And in our case, 5 fully connected layers will do a pretty good job for the decoder function. And if you're familiar with the machine learning literature, you probably realize that what we're doing is nothing but building an implicit neural representation for the deformation map from mechanics. Implicit neural representations uses a neural network to represent an arbitrary spatially dependent vector field, and each latent space vector here corresponds to a particular state of the represented vector field. For example, we can use implicit neural representation to represent the geometry of an object. In this case, it's a sign distance field. Neural representation can also be used for volumetric rendering, as it is in nerve or neural radiance field. So basically, this is a representation that is well explored in the machine learning community, and people have found this new representation to have lots of memory, continuity benefits. And we are basically doing the same thing, but in a model reduction context. So now that we have this trained neural representation, how can we run new simulation or new dynamics on it? You train your simulations on lots of data. Now you want to, okay, now I want to change my material parameter. I want to run a new simulation. How do we actually do it? To run new simulations, we only need to involve in this low dimensional latent space. How do we actually update it? We do so in 3 phases. First, run a network inference to get the full space information. Second, time step the full space information to update the vector field from f time step n to n+1 according to the PDE. Everything here involves just physics, no neural network, no approximation. And third, we invert the neural network to the reduced space. You might wonder, looking at this 3-step pipeline here, if we're going to the full space, how can we get any speed up? Aren't we just solving the original system? Well, this is a great question to keep in mind. As we'll see, instead of the original degrees of freedom, this entire pipeline here will only involve degrees of freedom from a small spatial subset. So let's first take a look at step 1. To obtain the full space information of an arbitrary point, we can just do a forward inferencing of the decoder function g, and we can obtain the corresponding gradient information by either differentiating the neural network, for example, via our differentiation or explicit chain rules. We can also compute the gradients through numerical approximations such as finite difference and finite element. And once we obtain the time step n information, we'll just do a time step update to get n+1 information. And for that, we do it with classic order update from our numerical analysis 101. Basically, for each xi, we solve for the f dot n+1 from the PDE. And this is also the place where we enforce the boundary conditions. And after that, we use our favorite time stepping method to update fn to fn+1. We can do this independently for each xi, so it is easily parallelizable and no neural networks involved. This step is completely physics-based, no approximation. We can respect all the physics laws we want. I should also mention that we're assuming an explicit integration here, but our framework can also be easily generalized to implicit integrations. Next, we took, yes.
Ask the question.
Yes.
Question from the audience.
Yes, please, I've been waiting.
So Fn, what is F?
F is the vector field you're interested. Any field like velocity field, deformation field, or temperature.
That are coming from. So we have a position mapping to that physical problem.
Yes, correct.
Do you want to go back a couple slides and make sure
Yeah.
people follow?
Yeah. So after training, right, we have a low dimensional representation of the complex system. And our goal is updating this guy to the n+1. Basically, that's how we solve dynamics. And the way we do it is we have to first go from here to infer, go from the x hat, the low dimensional space, to the full space. After we're solving PDE, we need to know the vector field information at this particular time step, the function value as well as the gradient values. And once we have this, we'll update the PDE in this full space. If it's the explicit method, then you can just update degree of freedom explicitly. If it's implicit time stepping, you have to do a solver there. And basically after this time step, we'll have the n+1 information predicted. We'll have the n+1 information predicted. And After that, we'll just go.
So you have the invariant, and from the invariant, you're gonna mathematically extract what the f plus 1 is?
So the way we upstate from n to n plus 1, right? This is using traditional solvers, you know.
Okay, so you have the invariant, and from that you can extract that.
Right. So this step here is not a, you know, lots of model reduction work, for example, you know, learn another like Hofmann theory, you know, like learns another operator to go directly from here to here without explicit PDE. But in our approach, we explicitly incorporate the PDE here because we think this approach will better conserve physical laws, as we'll see later.
What are examples of two? Maybe you can make two concrete.
Yeah, we can make two concrete, you know. For example, let's say we're solving the heat equation here, you know. So basically the vector field we're interested is, you know, U, right? And this is our PDE here. So for each xi, you know, we'll basically solve for the U dot n plus 1 by basically solving this, you know, assuming explicit integration for simplicity. You know, we have this from the you know, step 1, we infer the gradients of the vector field, and we basically, you know, this guy will be equals to this guy, right? So that's very straightforward. And then we'll just update, you know, update temporally using, you know, first order, you know, Euler integration. So basically, it's a very explicit PDE here. So now you have this newly updated, you know, n plus 1 vector field at some spatial, you know, locations. What we need to do is we have to basically invert the network. Now we have the output of it and find the corresponding input. And the way we do it is that we already have this information. Basically, we want to figure out a decoder function, and we want to figure out the x hat that's able to, once you pass this x hat into the decoder function here, should be able to predict this xn plus 1 information as closely as the one predicted by the PDE time stepping. In other words, our goal is to find a single parameter that fits all the data well. And for that, we turn to least squares. Basically, we want to solve for the xn plus 1 that align as closely as possible to the PDE, the field that PDE solver predicted.
Non-linear distribution, right?
Yes.
You use what's the name of Maron?
We use Gauss-Newton to solve this. Yeah. and the problem is here is exactly, you know, question. You know, if we do this naively, right? We'll basically require information of all the material points, right? Where all the spatial coordinates that we use in the training data. And if we're doing that, of course, it won't be fast at all. But luckily, you know, and for example, in this tower example, that's 3 million points, right? It's very expensive. And to address this issue, we notice that d hat, which is the dimension of x hat, is significantly smaller than NP here, which are the number of points, spatial samples we have. So basically, we're solving an overdetermined system here. And so what we can do is that instead, we can use just a subset of the original NP material points, and we denote this subset M. And in this target example, instead of 3 million points, you know, we can just use 50 points to do this inversion here. So this is, you know, and how can we obtain these 50 points, right? Obviously, how do we obtain the matters? We can either, in our experience, you know, stochastically sample in the space or through some greedy heuristic to optimally sample these points. So this is basically the how we get a computation saved is because we can just use 50 points instead of the original, you know, 3 million points to solve our PDE dynamics.
Sorry, back to my previous question about how do you get the initial x hat for the system. So do you assume that in the first step you actually have 2 steps so that you can actually infer the first x hat?
Yes, yes. So basically, you know, so this perfectly answers your question, right? You know, if you have lots of initial conditions, right? You have these points you want to fit, you can basically solve this problem and get you x hat, for example, or using the encoder to figure it out.
Also, question here. So,
Mhm.
if I understand correctly, the choice of the subset what's here will influence your factors.
Yes.
So, how
Yes.
do you ensure you have the characteristics you want?
Yeah, so that's a great question. So I think we have a demo showing, as we saw earlier, right? This demo here shows that this demo shows that, by using different spatial samples, right? For example, like if you use all the purple points as the training simulation is, you will be super accurate, right? One true is orange, and the blue one or the purple one aligns with the orange one really well. But it's computationally expensive. If you naive uniformly sample in the space, you would have very large error. So instead, we actually design an optimal sampling approach. So this is a greedy heuristics, where basically we just gradually add the sample set. We'll start with 1 point, and we choose for another point, see which one can improve the accuracy the most, and gradually add this point into our spatial sample set on the training data. So everything is pre-computation, and after we're happy with on the training data, on testing time, we can just use these samples to solve our PDE. Because we're solving over determined system here, we can use just a small spatial subset M to do this inversion. And because of that, we also only need the n+1 information for those in this spatial sample M. So this step also becomes cardinality of M, degrees of freedom. And similarly, for this step, we also only need information for the cardinality of M spatial samples. So this is really awesome because now the entire pipeline went down from the 3 million points we saw earlier to 50.
Why don't you go, if you train a model to go from xn to xn+1? How does that compare?
So if we basically train another operator that goes from
real network that goes from there to there.
Yes. So I think we have I think in the related work section, which is here. So for example here, right? So the first two approaches sort of adopt the very similar, but with the traditional classic representation, where they have to go through this sort of like 3-step pipeline where there's an explicit PD involved. And the second two approaches, which they call so our approach is what the literature calls the intrusive approach, and in the another approach is non-intrusive approach, which basically compute an operator directly update the low dimensional vector, and so is this work as well. So basically these are two families of approaches of handling this. And I think the benefit of this approach is that you don't need to know the underlying PDE, right? You get the data, you don't know what's the PDE, you don't know how to have access to the source code. But however, for this to work, you have to make certain assumptions. For example, this one here, you have to be able to prove that you can have a Koopman invariant subspace. So basically, that is not always true. But for our approach, we can work with any PDE system that you have without further assumption.
I understand. So
the point is,
if you have this and that, why? There's always some neural network that go between. No? You're saying that there's situations where there isn't a solution?
I think so. This one is using PDE neural network, right, to update the low dimensional space, completely fully data driven, right? And this approach is you update the latent space vector with a PDE in the loop, right? So there's two different approaches. Can you combine them in find a hybrid zone? I think so. For example, if you use the neural network to predict, and if the error is too big, you can always go back to PDE or something. Sounds good. So we have, what do we have? So we also show that because we have a PDE, explicit PDE form in our latent space dynamics, we basically were able to conserve the energy of the system. Basically, whatever conservation laws these PDE assume, we'll be able to capture them as well. And so here's just another example using this very fewer degrees of freedom to solve the system on image smoothing. And here is a fluid example where we can predict wide range of viscosities, interpolation, but also extrapolation as well outside the training range. This is true because the solution of these higher viscosity fluid, their solution lies in the space spanned by our low dimensional manifold that we train on. And our approach also works with solid mechanics. Again, reduce loss of dimension. And because of that, we obtain a very large speedup across different computing platforms on GPUs, data center GPUs, consumer GPUs, and also CPUs. And we achieved this computational speed up with only 1% error. And compared to prior digitization dependent ROM approaches, assuming the same latent space size, we obtain 26 times, we use 26 times less memory and 5 times less error. And here's an example predicting the deformation from different elastic modulus. So in this particular case, the training data contains not torturing, sorry, we don't torture animals, rotating this pig with different elastic modulus. We're the first model reduction framework working for point cloud simulation. Again, this is thanks to our digitization agnostic formulation. And we're no longer limited to matched data or grid data. And prior ROM approaches are contained to fixed digitizations. They face a dilemma between accuracy and efficiency. And our digitization agnostic approach allows for adaptive matching. So we change the match here as the contact happens. And as such, we obtain a massive speedup from the entirely high-res tree. And another feature of our digitization agnostic ROM approach is that, let's say we're training on this training data, we can actually directly run high-resolution simulation, which agrees well with the ground truth. And since the high-res simulation here is never exposed to the training process, we achieve zero-shot super resolution. And again, this is only possible with our digitization independent approach. Prior digitization ROMs cannot do this. So hopefully by now, we show some features of the CROM, but how does it compare with other machine learning methods? For example, physics-informed neural network PIN also represents vector field with neural networks. However, there's no dimension reduction in PIN, and the degree of freedom involved is still the same as traditional solvers. Therefore, it is computationally expensive, often slower than the traditional classic finite element method. And actually, if you replace this explicit dependence, PIN's explicit dependence on T with a low-dimensional latent space vector in our work, basically recover our reduced order simulation. So our work can be viewed as an intention of PIN for reduced order modeling. I think I'll skip the GAN part. So, great. What are some future opportunities? So for the first time, CROM opens the door for a unified machine learning framework for various digitized data. And I think we're really at the very beginning of this direction. Our vision is what we call kitchen sink training. And in this vision, we're aimed to build efficient reduced order models for arbitrary geometries, materials, and deformations. In summary, my thesis proposed 2 generally applicable physics simulation frameworks. Each framework is orders of magnitude faster than the prior approaches. These frameworks cover a wide range of physics simulations, from discrete rigid body simulation to various continuous PDE governed simulations. And while this thesis focuses on these approaches, I would also like to acknowledge other great works in physics simulation. The physics simulation community is extremely disciplinary, drawing researchers from numerical math, high performance computing, and also domain experts. I was blessed to read lots of these works during this PhD journey. And since its very beginning, the development of physics simulation has been driven by applications. Present-day physics simulation really started gaining its momentum during the 1940s due to the need to model thermonuclear reactions. The early computers, including this one by John von Neumann, were developed exactly for the purpose of simulating physics. Today, there are an ever-rising number of applications requiring fast and accurate physics simulations, extended reality, personal robots, unmanned aerial vehicles, and artificial heart, just to name a few. For that reason, we're optimistic that these applications will spur another revolution in physics simulation technologies. And the best days are yet to come. So this is the end of the technical portion of my talk. I would like to thank a few people that made this defense possible. Thank you, Professor Spaghetti. Just kidding. Professor Greenspoon. If you know Eitan, you know he likes joking. After being supervised by him for 6 years, I think I picked up quite a bit of humor too. The number of jokes I crack, especially the bad ones, increases exponentially with the number of papers I publish. All joking aside, academia is a place where I often feel inadequate and out of place, yet I find encouragement from you. Thanks for allowing me to be part of your career-changing season. Thank you for sharing your own struggles as a professor. I appreciate that vulnerability. And I appreciate your efforts, stop or prevent me from publishing papers, submitting papers, per se, not publishing papers, but submitting papers that are not ready. It was hard for me at the moment, but that set a solid foundation for years to come. Your love for your biological babies, that is Eden and Aviva, and academic babies, that is papers, constantly inspires me. I consider you're my role model in both of them. Thank you. Next, I want to thank all my mentors, Ken, Kevin, Maurizio, Chauncey, Steve, Hod, and Joey. You guys are extremely helpful at different stages of my PhD journey. I would also want to thank my colleagues, without whom this thesis would not be possible. Thank you, Yang Hao, Brennan, Meiti, Raymond, Hiki, Wendy, Hongling, Jay Lee, Auntie, and Da. I would also like to thank my internship colleagues, early mentors, lab mates, classmates, and all my co-authors. I want to thank all my friends, far and near, especially my mental health counselor, Dr. Ann Goldfield, Redeemer community group members, Hu Yang, Tang Sicong, and my childhood buddy, Jason, who unfortunately passed away 3 years ago. Rest in peace, brother, I miss you. Last, I want to thank my family. Mom, thank you for instilling in me a love for math, physics, and coding, which is basically what this thesis is about. I'm lucky to have a mom who poured out so much of herself into my upbringing. Dad, thank you for being a cool and chill dad who always believes in me. And finally, Lisa, you're my wonderful wife, the best mom, and my proud social worker. Thank you for being the best listener and my #1 cheerleader. And above all, thank you for buying me this art class. I love you. What's that? He didn't contribute that much, to be honest with you. But I love you too, buddy. So with that, yeah, I would like to thank you so much for your time, and I'm happy to take any questions.